So two things I want to clear up before we move on. The first one, let me tackle the one-to-one question first, and then we'll talk a little bit about modular arithmetic before we launch into the exercise. So what does it mean for a function f? Let's say its domain is a set x, its codomain is a set y. What does it mean to say that that function is one-to-one? If. And so, Colleen, what you just said was that one colloquial definition, and it's a pretty popular one, is that, how did you say it? Every input has a different output?
Yeah.
So how would we make that more formal? For every x, and so we're thinking of those as the inputs, so they belong to my domain set, capital X. The output, f of x, belongs to y. And how do we capture this idea of difference, though? I think this is where people run into a little trouble formally. And
If x1 doesn't equal to x2.
okay, so if I have two different inputs, so there I'm going to have to say x1 and x2 both belong to the domain, and x1 is different from x2, then what do we need to conclude?
Well, I was going to say that every x has, like every input x has a unique output y.
Let me put that observation up here on top. For every x in the domain, there is a unique f of x. All right, so somebody... Are we saying the same thing there? So we've got kind of two things going on, and I think this is why it tends to get confusing sometimes, is that the definition of one-to-one is that two different inputs, x1 different from x2, need to have different outputs. So f of x1 needs to be different from f of x2. And that's something that's not true for all functions, right? So, for example, f of x equals x squared. Is that one-to-one or is it not one-to-one if it's thought of as a function on, let's just think of it as a function on the integers for right now. Not one-to-one, why not? What's the counterexample to this assertion?
Mistake -2.
Yeah, f of minus 2 and f of 2. 2 is different from minus 2. That's something we will convince ourselves of right now, but in a few minutes we might not say that anymore. But anyway, 2 is different from minus 2, and the two of those function outputs are in fact equal. Right? So different inputs, the same output. So this function is not one-to-one. But the statement I wrote up here at the top of the screen in white, when we're using the word unique, what does unique mean in mathematics? There's one. There's only one, right? So the statement at the top is saying for every value of x in the domain, there is one output value f of x in the codomain. Does f of x equals x squared satisfy that assertion?
Say that again.
Yeah. So f of x equals x squared, the squaring function on the set of integers. Is it true that for every integer x, there is a unique, there's only one value of x squared? It is true. If you give me an integer, I can tell you for sure this is the value of x squared for that integer, right? What is that the definition of?
That's just a function.
That's just a definition of a function. Right? So every function satisfies the statement we wrote here at the top. Okay? Because that's what it means to be a function. Being a function means never having to say you're sorry. No, being a function means that every input has only one output, one and only one output, right? And one and only one, as mathematicians speak for, unique, right? It's this idea of difference that powers one-to-one functions. So for one-to-one functions, two different inputs have to have different outputs. Each of those inputs is going to have only one output, but for a one-to-one function, different inputs lead to different outputs. By the way that this is written down here is very hard to work with in proof. Because if we're trying to prove this directly, we have to assume x1 is different from x2, which is not always an easy thing to work with materially. So very often, instead of working with this implication, we work with it by contraposition. What would the contrapositive of this statement up here, one-to-one function, what would its contrapositive look like?
Did it exist input have, maybe did exist an input that have the same?
You're thinking of the negation. So if we wanted to disprove that a function was one-to-one, which is what we did here, right? Show that there exists two different inputs that have the same output. I'm thinking of how we could prove that something was one-to-one using the contrapositive of this statement.
So not f of x1 equals.
Yeah, so not this implies not that. And those nots are nice because it turns inequality symbols into equal signs. Right. So the other way that you'll see this written, f of x1 is equal to f of x2, so the negation of this part implies x1 is equal to x2. So another way to think about that is if you tell me that there are two values of x that have the same output, then they must have had the same input, right? If f is one-to-one, that's the only way that that can happen. The only way that outputs agree is when inputs agree, okay, for a one-to-one function. And when these are functions on the real line and we can graph them, then we require that they pass the horizontal line test. Every output that we can hit is achieved by only one input. Horizontal line doesn't cross the graph more than once, Kate?
This